So, good afternoon, students. Welcome back to once again chemistry online classes. See in the last lecture, that is the lecture 8, yesterday I covered you very importantly valence bond theory, its postulates, right? Even lastly, types of covalent bond, that is sigma covalent bond and pi covalent bond, along with the dipole moment. Okay. That means with the help of dipole moment, one can determine polarity of the unknown molecule. And next, with the help of that, I defined you polar covalent bond and non-polar covalent bond, and then next valence bond theory. What is sigma bond? Sigma bond is a type of covalent bond which is formed by overlapping of two atomic orbitals along the internuclear axis or head-on overlapping. Okay. There are three types: SS, SP, and P and D overlapping. Right? Then what is pi bond? Pi bond is a covalent bond which is formed by sideways or lateral overlapping of two atomic orbitals. Right? Okay. But pi bond always, for pi overlapping, but the lobes should be perpendicular, and it is only seen in P and P overlapping, that P and P lobes should be what? Perpendicular to each other. Otherwise, orientation is not possible. Right? Okay. Now I will tell you once again example for oxygen. Oxygen is containing double bond and nitrogen is containing triple bond. You already know. Once again I will repeat that and we go for hybridization. See, for oxygen molecule group 2. Okay. Yesterday I told you one oxygen atom, because it was hurry. If you assume like this, px, okay, and this is py, and this is pz. This is for one oxygen. Like this another one, px, py, and pz bond. Right? O and O. See, you know that oxygen is having atomic number 8, 1s2, 2s2, 2p4. See, outermost electrons are 6. See, these are paired. Okay, these are also paired. 2p4, how you can write? 2px1, 2py1, 2pz1, 2px2. Last 2py1, 2py1. See, here what I want to tell you that here, see, px and py and pz. Suppose this can be interchanged as py, and this is as pz. This is as px and this is as pz. Okay, or else you can make it as px only. Now you see. Orbitals overlap like this. P orbitals are diagonal shape. Py orbitals. So what they will do now? See, these two, they come closer to each other. Okay, and overlap to form a what? Sigma. Later these two orbitals, they overlap sideways to form a pi bond. Like this I told you yesterday. O's double bond having two lone pairs. Okay, one sigma, pi, and these orbitals will not take part in bond formation. Right? Okay. That's about formation of oxygen molecule. That means, see, they overlap each other and form like this hybrid orbital. This is for overlapping of oxygen. One sigma, one like this. Go for very clearly, I will tell you. Orbital overlap for nitrogen, N triple bond N. As I told you yesterday, it's 2 pi and 1 sigma. Right? Now, let us see. For nitrogen, if you write like this, this is px, py, and pz. Like this, px, py, and pz. Okay, right. Just a second. Px done by shape. Right. First they both come closer to each other. Closer to each other and form sigma. Py, okay, and this py, they overlap sideways to form pi. Another pz also they overlap to form what? Okay, that is n triple bond n. One long that is 1 4 pi, 1 0 pi, 1 between sigma. Like this, the very small thing yesterday I told you, difference between even sigma 1 and pi 1. Right? Okay. Why I am telling this fact means, before going to hybridization, you should know this very perfectly. And remember, this px, py, pz, they can interchangeable. They are observed in three-dimensional region. Px can be interchanged by pz, we can write here py. The coordinates can be changed. They are interchangeable, remember. Don't worry. Right? Further we come to the hybridization, I will make it very clear. Right? Okay. Axial overlapping, sideways overlapping. Two sideways, one axial overlapping. Right? Okay. Now coming to hybridization. Before hybridization, phase in, phase out. Some things you have to remember. Phase in and phase out. Means condition for orbital overlap. Phase out. Now, phase in means when there are two s and s orbitals possible, this will form a sigma. Right? Sigma possible. Sorry. S overlap. Then one s and one p overlap. Possible. Okay, this is also phase in. But one s and one p orbital. This is called phase out. Phase is out. Okay. Right. But in once again, sorry, I will just draw this in phase out. One s orbital cannot overlap the perpendicular orbital. Perpendicular orbital. Right? This is not phase out. But one p, another p, they can overlap. Actually, this is possible. SS, SP, P and P, but not one S and P perpendicular orbital. Not possible. Remember. Then even pi overlapping is possible. Perpendicular, pi to pi. Perpendicular. This is sideways overlapping, that you know. This is phasing. But one will not overlap with the another, that is perpendicular axis. And also, one p orbital may not overlap with another horizontal. Also, these are the phase now. Okay? And remember, if it is px orbital, it can only overlap with the px only. Py only py. Pz only pz. Not px with py and pz. That's really not possible. Remember. Okay? S can overlap with only S. S and P. This is axial overlapping is possible, but sideways or lateral overlap not possible. Remember. Before going to hybridization, you should know this compulsorily. Okay? Phase in, phase in, phase in. Proper orientation, proper orientation, proper orientation, proper orientation. This is called improper orientation, improper orientation, and improper orientation. This is px and this is one somewhat pz, not possible. Okay? Write this perpendicular py, px, not possible. One s orbital, one perpendicular p orbital, not possible. These are called phase out. That means improper orientation. That means for orbital overlap also condition should be fulfilled. What? Proper orientation and similar energy. Very, very important point to be noted before going to hybridization. Okay? Right. Now after understanding this, once again valence bond theory concept regarding sigma bond and pi bond, what are phase in and what are phase out, what are possible orbital overlaps SS, SP, PP, and only P and P in a pi polar. Now coming to next, hybridization students. What is hybridization? To know this hybridization, compulsorily have to go through valence bond theory compulsorily. Now hybridization is nothing but it is a process of mixing up of mixing up of atomic orbitals of slightly different energy or similar energy. See, I am using the word slightly different energy or similar energy to form new hybrid orbitals of identical and equal energy. That is called hybridization. So this definition will come to know when I write types of the hybridization. Okay, let us see what are the types of hybridization. And by studying this hybridization, sir, why there is a need of concept of hybridization? Actually, valence bond theory will not give you regarding anything about the shape of the molecule, geometry of the molecule, right? That's why this hybridization, by studying hybridization concept, one can know exactly the geometrical shape of the polyatomic molecules. In order to understand geometrical shape of the polyatomic molecule, there is a need of concept of hybridization, which was given by Pauling. Okay, that is Pauling. Right. Let us see. What is this hybridization? As I told you, what is the definition? Intermixing up of atomic orbitals of nearly same or slightly different energy to form hybrid orbitals of equal and identical energy is called hybridization. So you won't come to know very easily. That's why I will show you the example. Let us see. For example, first one, sp hybridization. Second, sp2 hybridization. Third, sp3 hybridization. Fourth, sp3d hybridization. Even d orbitals also involved. Fifth, sp3d2 hybridization. Even sixth, sp3d3 hybridization. And last one, sometimes that is here only we can go sp2d, sp3d, sp3d2 and sp3d3. See here, combination of 1s and 1p only, 1s and 1p only, right? Result that what we get, 2sp hybrid orbitals. See, 1a, combining these two both, 2sp hybrid orbitals, right? Okay. Like this here, 1s and 2p. It is not p squared. Don't write sp2 like this. Is wrong. This is only correct. But read it as sp2. 1s 2p. Resultant 1 plus 2 3. How many? Or it is called 3sp2 hybrid orbitals. That means number of atomic orbitals undergoing combination is equal to number of hybrid orbitals, which is a very important characteristic of hybridization. Like this here, 1s3p gives 4sp3 hybrid orbital, 3p, therefore sp3, right? And here 1s2p and 1p, therefore total how many? 1 plus 2 plus 1, 4sp2d hybridization or dsp2 hybridization, we can write. Okay, we can also just write it as dsp. Remember, sp3d, 1s, 3p and 1d, that is 1, 3, that is 5 sp3d or dsp3 hybridization also we can. Okay, and then sp3d2, 1s, 3p plus 2d, total 6 sp3d2, sp3d2 or it is also called d2sp3 hybridization, d2sp3 hybridization. Lastly, 1s, 3p and 3d orbitals in the form So 7 sp3d3 or d3 sp3 we can have. Why I am telling all this fact means, see, these are the hybridization involved. For sp2 sp hybrid orbitals, for sp2 3, sp3 4, sp2d or dsp2 that is 4, sp3d or dsp3 5, sp3d2 or d2 sp3 6, sp3d3 or d3 sp3 7 orbital. That means, see how much orbital will combine, that much orbitals will be. Before combining, they are called atomic orbitals of nearly same or slightly different energy. After mixing up, okay, after mixing up, for example, let's see, in day-to-day life, if you mix in what milk, banana milkshake, that is only these are called hybrid orbitals. Okay, 2 sp hybrid orbitals. Before mixing, they are having totally different character. After mixing, both the characters of S and P will mingle here. Remember, that is important. ನೋಡಿ ಮಿಕ್ಸ್ ಮಾಡೋದಕ್ಕೆ ಬೇರೆ ಕ್ಯಾರೆಕ್ಟರ್ ಇರ್ತವೆ, ಮಿಕ್ಸ್ ಆದಮೇಲೆ ಎರಡು ಕ್ಯಾರೆಕ್ಟರ್ ಇಲ್ಲಿ ಹಂಚಿಕೊಂಡು ಬಂದ್ಬಿಡ್ತವೆ. ಓಕೆ, ಎಸ್ ರೈಟ್. ಬಟ್ ನಂಬರ್ ಆಫ್ ಅಟಾಮಿಕ್ ಆರ್ಬಿಟಲ್ಸ್ ಅಂಡರ್ಗೋಯಿಂಗ್ ಕಾಂಬಿನೇಷನ್ ಓವರ್ಲ್ಯಾಪಿಂಗ್ ಇಸ್ ಈಕ್ವಲ್ ಟು ನಂಬರ್ ಆಫ್ ಪ್ಯೂರ್ ಹೈಬ್ರಿಡ್ ಆರ್ಬಿಟಲ್ಸ್. ದೀಸ್ ಆರ್ ಕಾಲ್ಡ್ ಹೈಬ್ರಿಡ್ ಆರ್ಬಿಟಲ್ಸ್. ಆಮೇಲೆ ಬರ್ತಾವಲ್ಲ, ದೀಸ್ ಆರ್ ಕಾಲ್ಡ್ ಹೈಬ್ರಿಡ್ ಆರ್ಬಿಟಲ್ಸ್ ಅಂಡ್ ದೀಸ್ ಆರ್ ಪ್ಯೂರ್ ಅಟಾಮಿಕ್ ಆರ್ಬಿಟಲ್ಸ್. ಪ್ಲೀಸ್ ರಿಮೆಂಬರ್. Okay, this first point is to be clear. Now for sp hybridization, they are having fixed geometry, remember, geometry, right? For sp it is linear, and for sp2 triangular planar, remember, triangular planar. For sp3 tetrahedral, and here for sp2 or dsp2 generally it is square planar. Okay, square planar structure. Then here for sp3d trigonal bipyramidal structure, and for sp3d2 octahedral, fixed octahedral geometry. Okay, and for sp3d3 pentagonal bipyramidal. Okay, these are the fixed geometrical shape you have to remember. Linear bond angle 180 degree. Bond angle 180 degree. Bond angle, fixed bond angles. Okay, and triangular planar x of is 120. Tetrahedral 109 degree, 28 minutes. All now it has been changed to 109.5 degree in the NCERT textbooks. Okay, now dsp2 square planar all are 90 degree. Okay, 90 degrees, and here trigonal pyramidal 5 bonds are there. Out of 5 bonds, 3 equatorial bonds. 3 equatorial bonds, they are 120. 2 axial bonds, they are 90 degree perpendicular to each other. Octahedral, all 6 bonds 90. Remember, and pentagonal bipyramidal here 90 axial and remaining 70. 90 and 70. Like this, we have fixed bond angle. This is very important first basic of the hybrid. That means now you come to know what is the definition. What is the definition? Intermixing of atomic orbitals. See, that's why I told not 2 or more. I told you intermixing of atomic orbitals of slightly different energies. S is having different energy, P is having different energy. That's why slightly different energy or almost equal energy to form new hybrid orbitals of equal and identical energy, equal and same energy. Remember, that is called hybridization. In S orbital and P orbital, maybe 3 sp2 and sp3, and D orbital dsp2, dsp3, d3 sp2 or d3 sp3 or sp2d, sp3d, sp3d2, sp3d3. Remember, okay. Right. Now I told you geometry, fixed geometries these are linear, triangular, tetrahedron, then square, planar, triangular, trigonal, bipyramidal, octahedron and pentagonal bipyramidal. Now I will show you the geometry also one by one while discussing in detail regarding what? Regarding the shapes. How they will do. Okay, this is the table will help. Right. Now, what is the definition, students? What is hybridization? Hybridization is the intermixing of two or more atomic orbitals of nearly same energy or slightly different energy to form new hybrid orbitals of equal and identical energy. That is called hybridization. Okay. Right. Now, just I will what is first I will tell you hybridization involves only S and P orbitals so that you should not get confused. This is in total all hybrid including S, P and D orbital for hybridization. Okay. See. Once again, what is hybridization? What is the definition? Intermixing of atomic orbitals of slightly different or same energy to form new hybrid orbitals of equal and identical energies. Equal and identical energies is called hybridization. Okay, this is the definition. Now, what are the characteristics of this hybrid orbitals? Characteristics of hybrid orbitals. See, characteristics of hybrid orbitals. Very important. First one, hybrid orbitals. Number of hybrid orbitals. Number of hybrid orbitals is equal to number of atomic orbitals. Hybridization or undergoing hybridization. Both are if two orbitals are combined, resultant also will get two hybrid orbitals. S and P, 1s, 1p, 2sp, 1s, 2p, 3sp2, like that. 1s, 3p, 4sp3. Okay, just that's why I told you the big thing. This is one. Next, hybrid orbitals are a very important point. Hybrid orbitals are equal or equivalent in shape and energy. Exactly equivalent and energy. This is very important point. Okay. Next, hybrid orbitals. These hybrid orbitals are more effective in bond formation, chemical bond formation or bond formation than pure atomic orbitals. Okay, that very important thing. Hybrid orbitals, they orient in space in preferred direction, orient in space in preferred direction so as to give definite geometry. So as to give definite geometry. So as to give definite geometry and minimizing repulsion. Minimize repulsion and maximize stability. Maximize stability. Thereby minimize repulsion and maximize stability. It becomes stable. Very, very important. See, they will not orient in space like anything. They will orient in space in some definite fashion, definite geometry. So as to give definite geometry, thereby minimizing repulsion between bonding pair and thereby losing energy and becoming stable. Very, very important. That is what characteristics of hybrid orbital. Okay, these first four basic points you have to know. Number of hybrid orbitals is equal to what? Number of atomic orbitals that will go in combination. And these hybrid orbitals are equivalent in their what? Shape and energy both. That means geometrical shape and energy. Then hybrid orbitals are more effective in bond formation than the pure atomic orbitals. And these hybrid orbitals will orient, they will arrange in three-dimensional region, how in preferred direction, so as to minimize repulsion, maximize stability, thereby giving what? Definite geometry to the molecule. So that's why for sp definite geometry is linear, sp2 triangular planar, sp3 tetrahedral. Okay, that's why 1s 1p 2sp 1s 2p 3 sp2 1s 3p 4 sp3 hybrid orbitals. Sp linear, sp2 triangular planar, sp3 tetrahedral structure. Okay, for sp bond angle is 180, sp2 120, okay, and then sp3 109 28 minutes or 109.5 degrees. That is called normal tetrahedral angle. Right? This is for s orbitals. We move on next, sp2 square planar, all 90 degree. Right? Then sp3d trigonal bipyramidal, 5 orbitals, trigonal bipyramidal. Out of that, 3 are on equatorial plane and 2 are axial. Axial are 90, equatorial 120 to each other. Then sp3d2 octahedral. All 6 bonds are equivalent, they are 90 degree to each other. Okay, then sp3d3 lastly, that is pentagonal bipyramidal. Pentagonal bipyramidal. That means all 6 angles are 90, one is only 72 degree. Like this, for sp3d3 pentagonal bipyramidal, they will give definite geometrical shape, which is very, very important. Basic part of hybridization. The next one is the condition for hybridization. To undergo hybridization, first condition is atomic orbital, they should be half filled. You are always under impression that only half filled orbitals can take part in hybridization. No. Not only half fills, very important point. Half filled, right here. Condition for hybridization, which is very, very, very important. Condition for hybridization. First one is what? Orbitals containing these hybrid orbitals. Okay, this hybrid orbital, that means hybrid orbitals containing the valence shell. The valence shell of the hybrid orbital must be what? Hybridized. Valence shell of the hybrid orbitals must be hybridized. First condition. And you are always under impression that only half filled orbitals can take part in hybridization. No, not only half filled orbitals, along with half filled orbitals, even completely filled orbitals and empty orbitals also take part in hybridization. How, sir? Half filled orbitals containing what? Electrons with the opposite spin, that is, they will form a bond, pair up. But empty filled means lone pairs. The empty filled orbitals are just overlapped by lone pairs. And what I told another one, that is especially even completely filled orbitals. Completely filled orbitals by lone pairs and empty orbitals by ligand. They will form coordination compounds. Remember, second one, half filled, very important, half filled, completely filled, and empty orbitals. empty orbitals take part in hybridization. Take part in hybridization. Hybridization process. Very important condition for hybridization. And remember, in hybridization always sigma bonds and lone pair of electrons are involved, but not the pi. Remember, third condition in hybridization. In hybridization only sigma and the lone pair take part in bond formation. Then what about pi, sir? Pi bond will not take part in bond formation. Remember, very important point to be noted. That's why always sigma bond is stronger than pi bond. Point to be noted. First, orbitals, hybrid orbitals. That means that valence shell of the orbitals must be hybridized. Then half filled, completely filled, and empty filled. Half filled with pair up. Completely filled means lone pair of electrons, and empty means that is ligands overlap and form coordination compounds. Like this, they will take part in what? Hybridization, because you are always under impression that only half filled. No, even completely filled in case of lone pair of electrons, empty orbitals in case of coordination compound. They also take part in hybridization process. In hybridization, only sigma and lone pairs electrons are involved, but not pi bond. Pi electrons or pi bonds are involved. Remember, okay? Then in hybridization, excitation of electrons is not only a condition prior to hybridization. Remember, okay? Excitation of electrons is not a mere condition prior to hybridization. Lastly, that's why I told you this. These hybrid orbitals, not only are half filled, even completely and empty filled orbital, they will take part in hybridization process. And during hybridization, one thing important condition, they not only should be hybridized, they should have equal and identical energy. That's it. That's once again limitation for condition for hybridization. So now I will tell you one by one types of hybridization involving S and P, that is SP, SP2 and SP3 hybridization one by one. But before going to this SP, SP2 and SP3, you should remember this table very clearly. I will tell you the basic. This I have to remember, very important. Please see. What is SP hybridization? As I told you, one S, one P orbital, they combine to form two SP hybrid orbitals. Okay? Hybrid orbitals, which are what? Linear. Okay? Friends, just as it. One S means generally S orbital, right? And one P. One P, S and P. They will combine to see forming linear shape like this. Linear and bond angle is 180. This is SP and this is SP. That means after these two mixing, okay, the resultant hybrid orbitals are linear shape SP and SP2 SP hybrid orbitals. Remember, this is very important. Like this for SP2, 1s, 2p, 3sp2 hybrid orbitals. Hybrid orbitals. Okay? 2 hybrid orbitals, that is sp3 hybrid orbitals. See how? These are triangular geometry. Okay, that means 1s, px, okay, 1 py, the mix up. That means see, they will mix up like this. px, py. Okay, khichdi ho gaya. Okay, then after mixing hybrid orbitals, what they give? That's only triangular planar. Small holes we can write, but this is not necessary. This is what sp2, this is is sp2 and this is sp2. This will be what? Triangular planar. Okay. Then sp3. sp3 one s 3p orbital. They combine to form 4 sp3 hybrid orbitals. 4 sp3 hybrid orbitals. Okay, that is tetrahedral geometry. Tetrahedral geometry. Okay. Yes. Px, right? Py, right? And pz. They combine. See, px, py and pz. Hodgepodge mixing masala हो गया. बाहर अब फेंको बाहर आ गया. देखो टेट्राहेड्रल. This is sp3, 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 4, sp3, 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 sp3 has order making bond angle 109 degree 28 minutes. And here bond angle between these is 806. Triangular planar and this is tetrahedral structure. Right? Like this, basically first you should know this. If they ask you sp, suddenly picture comes to mind, linear. sp2 triangular planar. sp3 tetrahedral. Now I think you come to know the definition of what? Hybridization. What is hybridization? It is intermixing of 2 or more atomic orbitals of nearly or slightly different energy to form new hybrid orbitals of equal and identical energy is called hybridization. Okay? Alright. Now this is all about basics regarding hybridization, condition for hybridization, characteristics of hybrid orbitals, and this is for hybridization involving S and P orbitals. Remember. Okay? Right. So that's about hybrid, that is hybridization. Now let us okay. Now let us move on to first type of hybridization, that is. I'll tell you one example for sp hybridization for your syllabus. They have given you beryllium chloride, okay, and C2H2. Beryllium chloride and C2H2. sp hybridization. What is sp hybridization? It is intermixing of one s atomic orbital and one p atomic orbital to form 2 new hybrid orbitals. That is 2 new sp hybrid orbitals of equivalent identical energy, forming linear 180 degree. Okay, right. That means, so once again repeating, one s, one p, that is px. Okay, they will combine to form resultant what? Resultant like this. Okay, that is sp linear 180 linear. Now we'll give example. Formation of beryllium chloride. For your syllabus in theory, they have given you first example. Beryllium chloride, BeCl. So you know that beryllium chloride, beryllium is having atomic number 4, right? 1s2, 2s2, right? Ground state electronic configuration first. 1s2, 2s2. This is called ground state electronic configuration. See, there are 2 valence electrons, but for hybridization, what is actually compulsion necessary is what? Half filled orbitals, right? Completely filled orbitals only in case of lone pair. These are not lone pair. These are paired electrons, right? So then beryllium tried to combine with 2 chlorine atoms. 1s atomic orbitals of the electron get jumps to higher energy level, making it a for hybridization by valent. Okay, see. Excited state EC, electronic configuration of beryllium, excited state. Now this 2s electron get excited to 1s to remain same. This will become 2s1, jump to higher energy level 2px1, right? 2px1, making it violet. Now see, two orbitals, half an orbital ready for beryllium chloride. Because how many atoms are there? 2 atoms, therefore violet. Right? Okay. See, first underline ground compulsory. This is first step. Ground state electronic configuration GEC. They are paired, but for hybridization, what is necessary? After orbital. So when two chlorine atoms try to combine with beryllium, 2s electrons of the beryllium get excited to 2p level, 2px1, 2py0, 2p0. Okay, making bivalent and necessary condition for hybridization. Now you know chlorine, one chlorine atom, you know one chlorine atom atomic number. What is the atomic number? Chlorine you will write here 17. 1s2, 2s2, 2p6. This is completely filled. Now 3s2, 3p5. In 3s2, 3p5, see, chlorine 17. Just write neon 3s2, 3p5. 3s2, 3p5. We write px, py, pz. X2, y. This hydrogen. How many chlorines are there? 2 chlorine atoms. Like this another chlorine atom. That means 2pz orbitals of 2 chlorine atom. They are also half filled. These are also half filled. They overlap with this 2s and 2px, forming what? sp hybridization. Okay. Both chlorine atom. Therefore, what you will write here? Hybridized state. Hybridized state electronic configuration compulsory. Okay, hybridization. So just to see here, 1s2, right? 2s2, right? And this is 2px2. Okay, 2py0, 2pz0. What it become? 2px2. See here, 2s. Sorry. 2s and 2p orbital involved in bond formation. That's what sp hybridization. This you have to show. Okay. So these two electrons will overlap and get split up. Therefore, 2s, 2p. That's why sp hybridization. This you have to show. Compulsory. Okay. After this, now what you will do? Geometrical shape. It is important. For that, you will take the hypothesis. Beryllium at the center. Okay, now 2 sp orbitals. This is sp, that is sp. Okay. Now they overlap with what? Pz, 3 pz orbitals of chlorine. 3 pz 1. Like this another chlorine 3 pz 1. They will overlap. But p orbitals, you know that they are dumbbell shape. How they will overlap? Axially. That's what here is just. They overlap axially like this. This is important. This is our overlap axially. Overlap axially. Okay, thereby forming beryllium. This is one sigma bond. This is another sigma. So sigma, making bond angle 180. That is what linear. This is how we are going to explain formation of molecule. This is one best example. According to our NCERT syllabus, see, they have given you this one. Beryllium chloride. Right? This carries 3 marks, compulsory question for annual examination. Once again, I will tell you. First, what you will write? Ground state electronic configuration of the central atom, beryllium 4, 1s2, 2s2. For hybridization, they are paired not satisfied condition. Therefore, when 2 chlorine atoms try to combine with beryllium, 2s electron get excited to higher energy level, making it bivalent condition satisfied for hybridization. Now each chlorine atom having one half filled orbital, that is 3p orbitals, they overlap along internuclear axis with the 2s and 2px forming 2sp hybrid orbitals. Okay. Excited state you have to write, then hybridized state compulsory you have to write, you have to show like this here. Then geometrical shape, simple. Geometrical shape you have to remember. Take this, sp, hybrid orbital, ready for hybridization. They overlap with what? 3pz orbital. P orbitals are dumbbell, that's why I have drawn this dumbbell. Along internuclear axis, not sideways. They form sigma bond, forming linear shape with a 180 bond angle. Okay? Like this you have to explain in the examination stepwise 3 marks. 1, 2, 3, this carries 2 marks and geometrical shape along with the bond angle 1 marks. Compulsory. Okay? Right. Now coming to next. Another example, C2H2. C2H2 they have given you for your syllabus. But we won't discuss now today because you will get confused. This much is enough. Today as per where hybridization is concerned. That means today what you learn, students? Definition of hybridization. What is hybridization? It is the intermixing of two atomic orbitals of slightly different energy or same energy to form new hybrid orbitals of equal and identical energies. Okay, generally s orbital and p orbital there are 3 types: sp, sp2, sp3. sp linear, sp2 triangular planar, sp3 tetrahedral. sp bond angle 180, sp2 120, sp3 109 degree 28 minutes or 109.5 degree. Linear shape, triangular planar, tetrahedral structure. These are at your tip of tongue, which are very helpful even for your hydrocarbons in organic chemistry. This chapter hybridization is very important concept both for organic chemistry as well as for inorganic chemistry also. Please be sure, that's why I am going very slowly. Right? Each and every step point is very important here. So one example I explained you today, sp hybridization of what? Formation of beryllium chloride involving sp hybridization. First step what you have to do? Write ground state electronic configuration of central atom. Then check for condition for hybridization. If it is not there, excite it to higher energy level. Make it bivalent, trivalent, tetravalent depending upon the atom. It will be different for different atoms. Okay? That depends upon combining atoms. Then after excited state, hybridized state. Then go for what? Geometrical shape. Over. Right? Right. Now I will stop here today. So tomorrow's class I will tell you another example of this sp hybridization, that is C2H2 acetylene molecule. Then sp2 hybridization, best classical example of for your NCERT textbook, boron trichloride. Then another complementary for that C2H4. This is ethylene or ethene, right? Acetylene or ethine. Then next for sp3 hybridization we have single saturated compound methane. That I will tell you tomorrow. Okay? Not make you confused. Right. So that's about hybridization, and have a nice day and enjoy the day. So this is enough for today. So bye from PANCHNATH. Enjoy the day.